If we have a progressively measurable process, then it makes sense to evaluate the process xt at a random time t equal tau. And in fact, if that tau is a stopping time, then progressive measurability is precisely designed for that new random variable x tau to be nicely measurable. But measurable where? What can we say about the sigma field with respect to which x tau is measurable? Well, taking our cues from the discrete time setting, lecture 45.3, we'll now define the stopped sigma field, f tau. If tau is any f infinity measurable random variable on our filtered probability space, taking values in the positive or infinite reals, we define, as in the discrete case, f tau to be the set of all events A measurable in f infinity, for which the event that the time tau is less than or equal to t intersected with A is actually in ft. And that's for all t less than or equal to infinity. Of course, the t equal infinity case is automatic here, since A is in f infinity. Now, since we know in the case where the filtration is not right continuous that there will be subtle differences between stopping times and optional times, we may also need to consider what happens with the augmented sigma field, and let's do that now. Let's define f tau plus to be the set of all events A in f infinity for which the event that tau is less than t intersected with A is in f tau. Notice that the event that tau is less than t is contained in the event that tau is less than or equal to t. That means that this constraint is harder to achieve than this one, and so we do get containment like this, which we would hope from the notation holds true. It's easy and routine, following the same arguments that we saw back in lecture 45.2, to show that these are both sub-sigma fields of f infinity. Now let's note that we might have thought that f tau plus should refer to a different sigma field. After all, we do have our augmented filtration, and it would make sense to use this notation alternatively to refer to this construction here with respect to that augmented filtration. That is, the set of all events A for which the event that tau is less than or equal to t intersected A is in ft plus for ht. Well, in fact, there isn't a collision of notation here because those two things are equal to each other, at least if tau is an optional time. And that is going to be one of your homework problems to show. Now, the first result, mirroring what we saw in the discrete time setting, is that if tau is a stopping time, then tau is f tau measurable. So that is, this sigma field is contained in here. If it is only an optional time, then we may need this larger sigma field, f tau plus, to get measurability. I'll just consider the stopping time case here. The optional time argument is almost exactly the same. If s and t are both non-negative times, then if we look at the event that tau is less than or equal to s intersected with the event that tau is less than or equal to t, well, first of all, that's equal to the event that tau is less than or equal to the minimum of s and t. But since tau is a stopping time, that's in the sigma field at time s min t, which is contained, of course, in the sigma field at the larger time ft. Now, notice that for any s, the event that tau is less than or equal to s is in fs, since it's a stopping time, and that's contained in f infinity. And so therefore what we've shown is that for any such s, this f infinity event, tau less than or equal to s, which I guess we should call A, matching the definition above, intersected with the event that tau is less than or equal to t, is in ft. So that shows that that event A is indeed in f tau. That is, what we've shown is that for all s, the event that tau is less than or equal to s is in f tau. And since tau is taking values in the positive reals that is equipped with the Borel sigma field that is generated by intervals of the form 0 up to s, it therefore follows that tau is f tau Borel measurable, which is what we wanted to show. So tau is f tau measurable, but what about the random variable x tau? Well, again, x tau is only a random variable if we assume that our process is progressively measurable. That's how it was defined. And in fact, in that case, conditioned on tau taking finite values, we do find that x tau is f tau measurable. Here's the precise statement, starting with our general filtered probability space. If tau is a stopping time and x is a progressively measurable process, valued in our metric space S, then x tau is f tau measurable on the event that tau is less than infinity. I'm writing it this way for convenience, just to notate. If I have any sigma field f and any measurable set b in that sigma field, we denote by f in brackets b to be the new sigma field over the restricted universe, the set of all a intersect b, for which a is an f. And that is a sigma field over the set b. And of course, we'll have a comparable version of this statement for optional times, where we have to replace the f tau with f tau plus here. The proof will be virtually identical, so we'll restrict our attention to this case for now. So we're going to have to use progressive measurability here. Let's use that definition judiciously. For any time t in 0 up to infinity, we'll define two maps. There's the map phi t that we've dealt with before. That's the map of t and omega separately in the process xt of omega. And let's also consider the map psi t, which is going to be defined for now on the event that tau is less than or equal to t. And that's just the function tau of omega, comma, omega. So it's tau cross the identity. That means that if we compose phi t with psi t, we get x tau. Now, if A is any event in the sigma field f at time capital T, and if little a is any time in the interval from 0 up to t, then if I look at the preimage of this function, psi t, of the event, the interval from 0 up to a, crossed with the event a in our sigma field at time t, that is just by definition the event that tau is less than or equal to a intersected with a, since we have to have both this in here and this in here. But a is less than or equal to capital T, so that's contained in the event that tau is less than or equal to capital T, intersected with a. And since tau is a stopping time, this is in ft. And in fact, since a is in ft, this is in the sigma field ft, restricted to the event that tau is less than or equal to capital T. Since that holds for every capital A, what we've shown is that this map, psi t, is measurable from this sigma field into this one, which is generated by sets of this form. Now we'll use progressive measurability, which is the statement that this function here is measurable from the Borel sigma field 0 up to t, product with ft, into the state space sigma field. So combining that with this statement here, we see that the composition of these is measurable from here to here. But this composition is just x tau on the event that tau is less than or equal to t. So in particular, if V is any measurable subset of the state space, if I take the preimage of the random variable x tau on that set V intersected with the event that tau is less than or equal to t, that's equal to the set of outcomes for which tau of omega is less than or equal to t, and x at tau of omega is in V. And as we just said, on this event, this can be construed as this composition. And that's the intersection of the event that tau is less than or equal to t with the preimage of that composition on V. We just showed that this map is measurable into here, which tells us that this is in ft, and of course so is this since tau is a stopping time, and so this is in ft. That is to say, for every time capital T, this event here intersected with the event that tau is less than or equal to t is in ft. That's what it means for this event to be f tau measurable. And of course, also this preimage only contains points for which tau is less than infinity, so we get this containment automatically. And so that shows that x tau is actually measurable with respect to this restricted sigma field on the event where tau is less than infinity. So we've constructed our definitions well. The stopped sigma field f tau is precisely a place where the stopping time tau is measurable, and the random variable x tau is measurable, at least on the event where it is finite. Now, before we move on to use these constructs, let's revisit all of the nice properties of stopping times and stopped filtrations that we studied in the discrete time setting here in the continuous time as well. I've collected all of those properties here, being very careful to state when they hold for stopping times or for optional times, or a mix of the two. Again, in most cases, in fact all cases that we are interested in, we will augment our filtrations to be right continuous from the start, and so stopping and optional times are the same thing. So we can mostly ignore those subtleties, but it's good to have them in the back of our minds when needed. I'm going to state all of these results here for you. The proofs in all cases are either identical to the discrete time ones or follow from them with simple limit arguments. And so I will then refer you back to that lecture or to the appropriate section of Driver's Notes for the proofs of these routine statements. If sigma and tau are stopping times, then so is their sum. And in fact, there's a stronger statement. If they are only assumed to be optional times, but they are both known to be almost surely strictly positive, then their sum is a stopping time, owing to the fact that there is a subtle difference, especially at time 0, between stopping and optional times. If sigma and tau are stopping times, so is their maximum and their minimum. And if tau n is any sequence of optional times, then their supremum, infimum, lim sup, and lim inf are also optional times. If we assume they're stopping times, then their supremum is always a stopping time. The other ones need not be, however, but they will, by what we said above, always be optional times, since any stopping time is an optional time. And as for the stopped sigma fields, if I take 2 stopping times, then 1, on the event that tau is equal to a fixed time t, the stopped sigma field f tau is the sigma field ft. And in fact, you can also quickly check that if we take the stopping time to just be the deterministic time t, then the stopped sigma field is the sigma field ft, as in the discrete case. If sigma is less than or equal to tau, then the stopped sigma field f sigma is contained in the stopped sigma field f tau. If we restrict the stopped sigma field f sigma to the event that sigma is less than or equal to tau, that's contained in the stopped sigma field at time sigma min tau. And so in particular, the events that sigma is less than or equal to tau or sigma is less than tau, or their complements, are in the sigma field f sigma min tau. And that sigma field, f sigma min tau, is the same as the intersection of the 2 stopped sigma fields, f sigma and f tau. Those are all statements about stopping times, and they're also all true for optional times, provided that we replace every instance of an f with an f plus. We're now going to turn to using these stopping and optional time constructs to try to learn more detailed properties about Brownian paths and other continuous time stochastic processes. And our first stop in doing so is to upgrade the Markov property to the strong Markov property in continuous time.